much more depth. But because you have seen it already, in one word, when you calculate the derivative, you're calculating the slope. Very good. So derivatives and tangent lines. The slope of a tangent line of a function at point x is otherwise known as the derivative at x, or the slope of the curve at x. So finding the slope of the tangent line of the given function at the given point. So here we have a function. What type of function is it? Quadratic. And we're specifically looking for the slope of the tangent line at 1, 5. So I'll give you a quick visual of what we're doing. T squared plus 4t. Whoops. X squared plus 4x. There's our image of the function, and we're going to look for the slope of the function or the slope of the tangent line at 1, 5, which is up here somewhere. So if you just want to sketch that quickly to wrap your head around what's going on, 0.15 is approximately there. And our tangent line looks like that, approximately. And the slope of the tangent line will be the instantaneous slope of the curve at that location. And so once we find the slope there, we're going to write the equation of the tangent line. So in order to write the equation of any line, we need the slope of the line, which we're going to find when we find the derivative. And we need a point on the line, which we already have, 1, 5. So to review how to find the derivative, we can in general find h prime of t, and that is going to be calculated looking for our limit as h approaches 0. It would normally be f of x plus h, but in this particular case it's h, so it would be h of t plus h minus h of t all over h. So when we start cruising through this, we have the limit as h approaches 0. A little bit confusing because there's two h's going on. There's the h that's the title of the function h, and there's the h that's approaching 0, which is kind of when you have that, the 2 points creating a secant line pinching together. So the h of t plus h just comes from us plugging in a t plus h for the function. So that, and I like to put that in brackets, that'll be a t plus h squared plus 4 times t plus h. That's my h of t plus h. Minus h of t is just minus t squared plus 4t. All over h. We're going to start ironing all of that out, keeping our limit as h approaches 0 there, because direct evaluation is just going to be indeterminate right now. So my numerator is going to become t squared plus 2th plus h squared. That's from squaring out my t plus h. Distribute your 4, plus 4t plus 4h, and distribute your minus sign. Minus t squared minus 4t all over h. Still, we would get 0 over 0. So combining like terms is going to cancel out our t squareds. T squared minus t squared is gone. Positive 4t minus 4t is gone. And then the 3 terms left in my numerator all have an h in them. So I can divide the h out. So limit as h approaches 0 of 2t plus h plus 4. Any questions so far? Okay. So now that that denominator canceled, I can go ahead and find the limit as h approaches 0. I plug in a 0 for h. This is just going to boil down to 2t plus 4. So start to finish, my derivative formula is that h prime of t, so the slope of my h function at any given t value can be computed just by plugging that t value into this expression 2t plus 4. So for this one, we're trying to evaluate h prime where? H prime of 1, because that's my x coordinate. So h prime of 1, in other words, the slope of this function at an x coordinate of 1 is 2 times 1 plus 4 is 6. So my slope right there is 6. And then we can also write the equation of our tangent line. We have a slope of 6 and a 0.15. The easiest way to write the equation of a line is using point slope formula. So y minus y1 would be y minus 5 equals m. And then x minus x1 would be x minus 1. And there's the equation of your tangent line. If you wanted to, or if the directions said to, and they required slope-intercept form, this is point-slope form, slope-intercept form, you would just have to distribute your 6 and then add your 5 over. And actually, you may want that format just for the sake of looking at it on your calculator. If I now plug in what is supposed to be my tangent line, I'll see a tangent line come up. And it's hard to see it there, but if I were to zoom out a little bit and do like negative 20 to 20, it might be a little bit clearer that that red line skims the blue line at just that one location. Yes? You could zoom in even further to the 0.15. In that general vicinity. And there's your parabola, and here's your tangent line. Good? You can keep zooming in if you want. There's my parabola, but it's hard to see because the more you zoom in, the more the parabola looks like a line in and of itself. But questions on that? Remember that whole process? F of x plus h, we'll write this at the top. So in general, f prime of x equals the derivative of a given function f is the limit as h approaches 0 of f of x plus h minus f of x all over h. And that will give you, once you iron that all out and find the limit, that'll give you an equation used to find your slope at any given point in time. Okay? So the quadratic one, we've done a lot of quadratics with this format, so a lot of that squaring of the binomial and stuff happens second nature at this point. But there obviously are difficult ones, more difficult, because you're having to plug in x plus h to this. So we'll find just the derivative. So f prime of x, we will calculate by doing the limit as h approaches 0. What will f of x plus h look like here, Sarah? Good. Here's f of x plus h. Minus f of x is just subtracting the function all over h. Now, the brackets there aren't as helpful as they are when you're plugging into a polynomial. Because when you're plugging into a polynomial, you really need that degree of separation so that you make sure you distribute your negative. We wouldn't forget to distribute a negative here because it's not a polynomial, so there is no distribution per se. So something like this is going to give us 0 over 0, but like squaring things out and simplifying polynomials is not the way it's going to work because there are no polynomials, but we would get indeterminate. And so our manipulation here would consist of what? In what ways do we manipulate? Sometimes we just simplify things out and reduce. Sometimes we factor and cancel and reduce. What are our other methods of manipulating? Come on, Mackenzie, I know you know it. Remember when your teacher gave you this awesome thing? Indeterminate cases. Manipulate by simplifying the direct evaluation. You can rationalize. You can factor and cancel. You can clear complex fractions. What would this one have? I actually think this one was on your last test. It was a radical one like this. How are we going to manipulate? Can we factor? Can we rationalize the numerator? Olivia? Okay, so you could try to rationalize right now. Let's do it that way. I would probably, because there's complex fractions as well, I would probably start with that. It's going to be easier, but let's see what happens. It's a good learning opportunity. So ideally, and we'll come back if we have to, maybe you just want to watch what happens in case we have to retract. But if that's what you saw, because radicals make you think of rationalizing, if she were to multiply by the conjugate, that would be 4 over root x plus h plus 4 over root x on the top and on the bottom. See, the problem is you're spreading around that nasty complex fraction, but we'll try it. So that would be 16 over x plus h. Your outer and your inner cancel, minus your last two would give you 16 over x. And your denominator would be h 4 over root x plus h plus 4 over root x. So the issue here now is complex fractions. And now we have 4 mini denominators to worry about versus 2. So that's just going to get way uglier than it's worth. So I am going to back it up. I'm just going to clear the fractions first, and then if we still have radicals to worry about, then I'll worry about them. So of our 2 mini denominators, the denominators are root x and root x plus h. So that's what I multiply the top by, and that's what I multiply the bottom by. And in the numerator, I'm going to actually distribute that. So when that gets distributed to the first fraction, your root x plus h's are going to cancel, leaving you with just 4 root x. And when you distribute to your second term, the root x's are going to cancel, leaving you with minus 4 root x plus h. All over h root x plus h. And all the while with your limit as h approaches 0 out in front. And if you wanted to now, you could see, can I plug in an h of 0? Or I'll still get 0 over 0. So it's not good enough. Now that you've gotten rid of complex fractions and radicals still exist, multiplying by the conjugate would probably be the way to go. Okay? So that would be up top, 4 root x plus 4 root x plus h. And on the bottom, 4 root x plus 4 root x plus h. On the top numerator, we're going to distribute. We're going to get 16x. Because they're conjugates, your outer and your inner will cancel. And your last is going to give you minus 16, the negative 4 times the positive 4. And then the root x plus h times root x plus h is just x plus h, which has to go in parentheses. If it doesn't go in parentheses, you're not going to be multiplying the 16 by the entire binomial like you should be. And then your denominator, we weren't rationalizing our denominator, so I'm just going to keep it as this very long process. Keep simplifying that numerator. It'll be 16x minus 16x, and then minus a 16h. So the 16x and the 16x will cancel, and it'll just be minus 16h up top, with h root x plus h, and then 4 root x plus 4 root x plus h. And then in the numerator you have h, which is the part of a monomial, and in the denominator you have h, which is the part of a monomial coefficient. So those cancel, and now we can plug in an h of 0, because the h over h, which was responsible for the 0 over 0, is gone. So when we do that, we'll get negative 16 up top. Our denominator, just to show it all out, will be root x plus 0, parentheses 4 root x plus 4 root x plus 0. And I've taken off that limit as h approaches 0 because I've already plugged in 0 for h. So that's negative 16 over, what's root x times root x? X. And 4 root x plus 4 root x. What's 4 root x plus 4 root x? Joey. 8 root x. Probably you'd see the 8 and the x out in front flip spot, so it would be a coefficient of 8x root x. But the negative 16 and the 8 reduce too, to negative 2 over 1. So negative 2 over x root x. And that's how you would calculate the derivative at any given point on that curve. Just out of curiosity, at what types of x values will this be undefined? Will the derivative not exist? Because the limit won't exist. When will that not exist? If x is what? Negative or 0, right? Now the reason is, here's your original function. When you look, oops, I gotta get rid of this window. When you look at this function, why doesn't the derivative exist at negative numbers? Because the graph doesn't exist at negative numbers. Why doesn't the derivative exist at 0? Because the graph doesn't exist at 0. As soon as you get beyond 0, what could you tell me about the slope here? Is it positive or negative? As soon as you get past 0, is that a positive slope or a negative slope? Negative. Steep or not so steep? Very steep, right? In fact, can we all agree that the slope is always negative? Why will this always have to be negative? What's that? Because the numerator is negative and the denominator will only work if x is positive, right? So it's always going to be a negative over a positive, which is why this is always negative. Now, if you're plugging in just after 0, like a teeny tiny number, you're going to have negative 2 divided by teeny tiny numbers, which is negative infinity, right? It's a very steep negative slope. Gets infinitely steep, truthfully, in the negative direction. And then if you plug in a big x value, not that 10 is big, but just for the sake of seeing it, negative 2 over 10 root 10 is like negative 2 over 30-ish. And negative 2 over 30 is negative 1/15. The slope of negative 1/15 down 1 over 15 units is a pretty shallow slope. Does that make sense? Okay. So you know, there are a lot of different notations for the derivative of a function. If a function is written as f of x, f prime of x means the derivative. That's the one we've been using most often. If a function is written as y equals, like if instead of f of x equals, it said like y equals 4 over root x, then dy dx is how they would maybe write the derivative. Or they would say y prime. So this and this are the same, pretty much. If it's f of x equals, then f prime is the most concise way of writing it. If it's y equals, then y prime is the most concise way of writing it. But so, like this other way, dy dx is like the an equivalent. If it's y equals, rather than writing y prime, they might write dy dx. And that's all this one is too. If it's f of x, rather than doing f prime, they might do df of x dx. Like that's the same thing as dy dx. Everybody see that? So just different notations. Nothing that you do is different other than when you see those notations, know what they mean. And then this one is used most infrequently, in my opinion, where there's a subscript of the x. So it's the derivative of the y equals function with respect to x is how you would say that. So right now we only have two variables floating around. We have the y equals, and so we're always finding the derivative of y or the derivative of f of x with respect to x. This one up here would technically be, here's your different notations. You could have h prime of t. That's the derivative of the h function with respect to t. You would have dh dt. That's the derivative of the h function with respect to t as well. Do we follow that? You could have just, sort of hard because it's not. You could just have h prime. But right now we're just finding the derivative of the function with respect to the only other variable that's in there. Eventually we will get to a point where there's multiple variables. So that's really what this dx is. It's the derivative of your y function with respect to x. Derivative of your f of x function with respect to x. Derivative of your y with respect to x. Okie doke. What do we have on the back? All right. We have a function, it's quadratic, and we have some line. Find an equation of the line that is going to be tangent to this graph, but parallel to that line. So this line is completely separate from that function. We're going to try to find the equation of another line that is parallel to this one, but tangent to this graph, okay? So I think we should start here because that's what our preliminary knowledge will help us with first and foremost. If we need to be parallel to this line, what does that tell us about our line? What should we find out about our line first? If we want to be parallel to this line, what do our line and that line have to have in common? Krista? Slope. So what is this one's slope? -4. It's a little too early to tell. You got to get y all by itself. So you'd subtract your 4x over and subtract your 3 over. So that line has a slope of -4. So our line, which has to be parallel to that one, also has to have a slope of -4. But now we're trying to find an equation of a new line that has that slope, but we need a point for our new line as well. And that's where your function is going to come in. We want to find the location where this graph has a slope of -4. Do you follow? We want to find the point on this function, it'll be our point of tangency, that has a slope of -4. So we need to find our derivative and set it equal to -4 and figure out at what x coordinate that's occurring. Does that make sense? So let's find f prime of x. And once we do that, we're going to set it equal to -4. And we'll actually figure out where this x value is. So our limit as h approaches 0, f of x plus h looks like that, minus f of x looks like that, all over h. I'm going to simplify that numerator by squaring out the binomial. And then distributing the 2. Letting the 2x squared minus the 2x squared cancel. Both terms have an h in it, so we can divide by h, and we're left with 4x plus 2h. And now that we've canceled out that denominator h, we can just find the limit as h approaches 0, which would make this what, Nate? 4x. So f prime of x equals 4x, and we want to know when that slope will equal -4. So at what x value, Morgan, will that happen? -1. So we found the location on this parabola where the slope was -4. And that happened at an x coordinate of -1. How would you find the y coordinate of that point? Nate? Was that a hand? Oh. Connor? To this line formula. Okay, hold on. That's actually not correct. I'm going to show you why. -4x minus 3. Okay, here's the quadratic we're trying to write a tangent line to. And here's the line that we're trying to be parallel to. Here's what this looks like. There's our parabola. And there's our line. Do you see how our line is missing the parabola slightly? Yes? We might see it a little bit more thoroughly if we do this. Ooh, okay. Just missing it, right? We want our line to be parallel to this one. So essentially, we're going to take that red line and pretty much we're trying to figure out how to slide it, right? Until it runs into the parabola at one and only one point. So we're trying to write the equation of this line that's just moved over a hair, right? And we just found that it's going to be at this point -1 whatever. That is the location where this parabola has a slope of -4. So the point, Connor, is actually on the parabola, right? We're trying to write the equation of a tangent line to the parabola. Then we need the slope of the parabola, which we have, and we need the point on the parabola at which that slope is occurring. And it's at -1 comma, you would plug -1 back into the function, and that will give you the point of tangency on the function. So that would be -1, 2. So slope of the tangent line, point on the tangent line, also has to be the same as the point of tangency that's on the function itself. Do we follow that? So writing the equation like this, y minus 2 equals negative 4, x plus 1. And just so I can type it in on the calculator to show you, I'm going to change it to point slope. Or I'm sorry, I'm going to change it to slope intercept. And you'll see now when I graph this third function, it's going to be parallel to the red, but it's going to be tangent to the blue. Negative 4, ooh, shoot. 2x squared, I don't want to get rid of anything. Negative 4x minus 2. So there's our parabola. There was our original line that we just needed to be parallel to. And then here comes the line that is parallel to that, but tangent to the curve. Any questions? Okay. This is going to be a new concept. We're given the graphs of original functions. We want to sketch the graph of what the derivative of that function at those locations will look like. So, if we're plotting the, and I'm just going to keep it underneath so it's kind of lined up. What can you tell me about the slope here? Between 0 and 4, what is the slope? Constant, specifically, can you tell me the value of it? But negative 1, right? It is, right. It's starting at 4 on the y, and it's ending at 4 on the x, so it's going down 4 over 4. So a negative 1 slope that entire time. So if we're going to plot the derivative function, we need to be at negative 1 this entire time. It's just the slope is negative 1, so that's why this is constant on that stretch. Does that make sense? Whatever the slope is here, that's where your points need to be on the derivative graph. Now, we've talked about this in the PreCalc book, but let's talk about it again. Functions do not have slopes at endpoints, so that's an open circle. Functions also don't have slopes at sharp corner points. So at 4 is an open circle. Because the slope changes drastically from this side of 4 to that side of 4. It's not a smooth continuation. It's not a smooth continuation from a constant slope of negative 1 to a constant slope of positive 1. Wouldn't you agree? There's no smooth transition there. It just drastically changes. Here the slope is negative 1 in this stretch, and then from 4 to 8, it's positive 1 in that stretch. So you've got the derivative, the graph of the derivative modeling what the slope numerically is of the original function. It was negative 1 between 0 and 4, and it was constantly negative 1, so we have a constant at negative 1 between 0 and 4. And it was constantly positive 1 between 4 and 8. So between 4 and 8, we're constantly just at a numerical value of positive 1. So what's interesting about this is what type of function creates this V shape? Absolute value. What you're giving me this one. So the derivative, what you can see here, you don't need to memorize this at all, but it might come up again, and it should make sense that if you look at an absolute value function and you want to graph the derivative of it, it's going to be a jump function. Because on one side of the V, it's constantly one thing, and there you get a flat line because it's constantly that slope. And then on the other side of the V, it immediately jumped quickly to another constant. Just sort of worth pointing out because we know that that's a jump function at this point. Good? Okay? This one is more of a smooth transition. Okay? still at -2 and +2, the derivative does not exist. So we will use open circles. Is there any location on here where you can tell me exactly what the slope is? Like the exact value as opposed to just positive or negative? Andrew? At 0. At 0, the slope is what? 0. So at 0, f prime is going to be at 0. What was it just prior to 0? Was this a positive slope or a negative slope? Positive. Steep or not so steep? Not steep. So it's in the positive, so that would mean above the x-axis, but not very far above the x-axis, right? And as you move further to the left, are we positive or negative slope? Still positive. Steeper than it was here. Agreed? So it's still in the positives as you move over, but even steeper, so that's going to be a higher numerical value than we were before. And it's gradually, as you're moving left, right? It's gradually getting steeper and steeper. So as we move left here, the derivative is gradually getting higher and higher. This is think of this as like the top half of the circle, right? So right when you reach -2 on a circle, if this was a circle with a radius of 2 centered at 0, 0, what would the slope be right at -2? If you were to do a tangent line, it would have an undefined slope because it gets infinitely steep, yes? So if it's getting infinitely steep with a positive slope, this is getting infinitely higher, yet right at -2, the slope does not exist. Number one, because it's an endpoint, but even if this was a circle, right? If this was a circle and it kept going, right at -2, the slope would still be undefined, and that's why the derivative graph can't exist at -2. What if it was, well, you couldn't do that. Never mind. You can't make it a circle because then it's not a function. And then over here, your slope is like slightly negative, right? And then it's getting more and more negative. So as you move towards 2 in this direction, it's slightly negative, so that's like maybe only a y-coordinate or a derivative of -1/5. But as you get closer to 2, it's getting steeper and steeper in the negative, so we're into the deeper negatives values for our derivative graph. And again, it would be like an asymptote at 2 because it's not existing, yes, because of the endpoint, but also because it's essentially becoming, for an instant in time, instantaneously, it's a vertical tangent. And if it's a vertical tangent line, the slope does not exist, which means the derivative does not exist, which is why the derivative graph will never cross that asymptote. Okay? So there's some heavy conceptual stuff there. We didn't get to that last problem, but it won't kill you, I don't think. And there's your homework on 131. Did I send out dates last week about your upcoming tests and quizzes? I didn't. I'll try to do that.